Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Nur Azwani binti Jamihe, my teammate Muhammad Ifan Faris bin Jamil, and also Nur Anis Husna binti Abdul Rahim. Today, we are going to present our mini project of the finite state machine on the multifunction steam ion system. In this project, the FSM of multifunction steam ion was modeled based on the Philips 3000 series ion model. This model have two major functions, which is the ion heating and the steaming function. Based on this table, we can observe that the ion heating function have two modes, which is the on and off modes. Meanwhile, the steaming function have three modes, which is the off, low, and high modes. The two functions of the multifunction steam ion was recognized as two input, which is M and N. Based on the recognition of the input and output of the system before, we started to construct the state diagram of the system. We start by defining the binary output of the ion heating and the steaming function of the system. Firstly, the ion heating input function, which is, we know that it has only two modes, which is on and off mode. So, we recognize the binary output of the off mode is 0 and the on mode is 1. Meanwhile, for the steaming binary output, we recognize with 2-bit binary output as it has three modes, which is off, low, and high mode. So the binary output will be 0, 0, 0, 1, and 1, 0. Then we construct the truth table, which consists of 6 states of the system, the state index, and also the output of the ion heating function, which is X, and also the output of the steaming function, which is YA and YB. Then, the state transition table was constructed based on the truth table. In the state transition table, we apply D flip-flop as the sequential logic of the system. The state transition table consists of current state, the input, which is M and N, the next state, the D flip-flop, and also the output of the system, which is X, YA, and YB. After that, the mathematical logic expression of the output was developed by the Karnaugh method applied to the table. Then, from the state transition table, we developed the state diagram of the multifunction steam ion system. Based on the generated state diagram before, we can observe that in the initial state, which is state 1, the ion heating element and steam generation will stay off. It will remain off if no input is received. When the M button is pushed, the heating element will turn on while the steam generator will remain off, such in state 4. If N button is pressed, it will go to state 2, where the heating element is off but the steam is generating at low mode. During state 4, if the M button is pressed again, the heating element will turn off and it will return to state 1 where all output is off. But if the N button is pressed, the steam will start to generate at low intensity with the ion heating element being on, such in state 5. At state 5, if the button N is pressed again, the steam generation will increase to high with the heating element is still on, such in state 6. But if the M button is pressed, it will lead to state 2. During state 6, if the M button is pressed, the heating element is turned off, turning to state 3, where the heating element is off while the steam is generated at high mode. However, if the N button is pressed, the steam generation is reset to off while the heating element is still on, thus it returns to state 4. At stage 2, when the M button is pressed, the heating element will turn on while the steam is at low mode. Thus, it turns into state 5. However, if the N button is pressed, the heating element is still off, but the steam generation will increase to high mode, making it move to state 3. At state 3, if button M is pressed, it will move to state 6, where the heating element is on and the steam is at high mode. But if N button is pressed, the steam generation will be off, while the heating element is still off. Thus, it returns to state 1, which is the origin state.
Oh, salah tekan batu lah. Assalamualaikum and warahmatullahi wabarakatuh. So for our project here, I'm going to explain the coding part of our FSM project. So we are using EDA Playground as our development software because it is much easier to use and it is available online. So first of all, on the right side we have the design.sv, which contains our module design. First of all, we have to declare our inputs and outputs. So we have the clock, the reset button, M button and N button as our input, and we have the iron heater and the steam generator as our output. And then we have to declare our states. We have 6 states. We have 6 states beginning from state 1 to state 6. And then we could go to the case statement. So the case statement contains the states and is built based on the state diagram as shown before. So we'll go through a few examples. So in state 2, if the M button, which is the iron heating button, is pressed, it will jump to state 5. But if the N button is pushed, it will go to state 3. So if at state 3, if the M button is pushed, it will go to state 6. And if the N button is pushed, it will go to state 1. So after the case statement for the change of states, we have the case statement for the output. So at state 1, as you can see, it is the initial state of the system, which means everything is turned off. So the iron heater would be off and the steam generator would be off. We'll go to, let's see, state 5 maybe. So at state 5, the iron heater will be 1 and the steam generator will also be 1. Indicating that the iron heater is on and the steam generation is at level 1. Okay, so on the left hand side of the window, we could see the testbench.sv. The testbench.sv is where we test our design to ensure that the output is as we expected.
So as for the result, the system state was presented by a wave with input M and N, output X, YA and YB. So the Verilog codes governs the system transition state, ensuring the accurate state transition. So the validation of the wave was conducted against the transition table, referring table 13.0. So the system exhibited the desired behavior during heating and steaming operation. So the simulation result confirmed the Verilog-based FSM system's efficiency, meeting the power consumption and performance targets. So the simulation results support the real-world application of the multifunction steam iron FSM system. So as for the conclusion, we aim to create a versatile and efficient control system for the steam iron, integrating various functionalities. So it developed a comprehensive FSM to model different state and transition, including heating and steaming modes. So to conducted extensive simulation and testing to ensure reliability of the Verilog model. So the system exhibited a robust performance under various scenarios, improving its effectiveness in real-world conditions. So the Verilog-based FSM system meet design objective by providing a reliable and efficient control. So the successful of implementation showcase the potential of the hardware description language in designing complex digital system, and this serve a solid foundation for the further improvement in household appliances control systems. Thank you.